The soft-top board, high-volume displacement. Its purpose is singular, maximizing positive buoyancy. The dense foam core allows for easier paddling speed, ensuring you reach the required wave velocity before the kinetic mass breaks. The wave peak, point of maximum energy. The wave breaks first at the highest point of elevation. Recognizing this is crucial, as it dictates the line of travel and the vector of the wave's kinetic release. The right of way, collision avoidance. Physics dictates that the surfer closest to the peak is in the primary energy zone. To enter a wave occupied by another is to fundamentally disrupt the fluid flow of the ride. The paddle stroke, hydrodynamic propulsion. Drag is the enemy of velocity. By slicing the hand into the water and anchoring the arm, the surfer uses their body as a fulcrum to pull the board forward, matching the wave's speed. The pop-up, explosive center of gravity transition. Transitioning from prone to standing requires a massive, instantaneous shift in mass. It is not a crawl, it is a violent extension of the limbs to lock the body into a stable, centered vertical plane. The safety leash, kinetic anchor. This urethane cord is the only physical link between you and the board. It is engineered to withstand hundreds of pounds of shear force, keeping the board from becoming a projectile. The rip current, fluid exit channels. A rip is a localized high-velocity channel of water moving seaward. Understanding this fluid path is essential. It is an efficient transport mechanism, provided you leverage the trajectory correctly. The impact zone, chaotic dispersion. This is the region where waves coalesce. The kinetic energy of the swell is violently dissipated here, creating turbulent, whitewater fluid conditions that demand immense physical effort to penetrate. The hydrostatic seal, thermal regulation. A wetsuit must function as a second skin. If the fit is loose, water flushes the interior, instantly destroying the trapped thermal layer and inducing rapid body heat loss. The athletic stance, static balance. Lowering the center of gravity while keeping the spine perpendicular to the board creates stability. It allows the surfer to absorb the violent vibrations of the wave face through the knees, not the torso. The turtle roll, surface area inversion. To penetrate a broken wave, you flip the board upside down. This minimizes the surface area presented to the wave's energy, allowing the massive volume of water to pass overhead. The duck dive, hydrodynamic penetration. To pass through an unbroken wave, the board is submerged. The physics requires timing. By pushing the nose down and using the knee to leverage the tail, you travel beneath the wave's kinetic force. The bottom turn, edge engagement. This is the transition from descent to ascent. By carving the board onto the rail, you engage the fin foil, creating lateral Bernoulli lift to project the board upward toward the lip of the wave. Energy dissipation. Falling is an art of kinetic management. To avoid board impact or reef contact, you must project your body away from the board and penetrate the water cleanly to minimize the surface tension impact. The wax application, coefficient of friction. Applying a lattice structure of wax creates micro bumps. These bumps create a high friction interface, allowing the surfer to lock their foot in place against the high G-forces of a turn. The longboard, maximum planing hull, engineered for low-velocity swells. The massive surface area provides immense primary stability and lift, allowing the rider to easily match the slower kinetic speed of unbroken, rolling ocean waves. Wave period, deep water kinetic spacing. This measures the time between swells. A longer period means the kinetic energy travels deeper in the ocean, creating a much more powerful, mathematically organized wave when it hits the reef. Bathymetry, seafloor friction. A wave does not break by itself, it trips. As deep water kinetic energy collides with the rising topography of the seafloor, extreme friction forces the water column upward, physically pitching the lip forward. Offshore winds, laminar face grooming. Wind blowing from land to sea opposes the wave's forward velocity. This aerodynamic resistance physically holds the wave open, creating a perfectly smooth, unyielding geometric wall of water for the rider. Onshore winds. Turbulent degradation. Wind blowing from the ocean violently crushes the wave's back. This destroys the laminar flow, instantly breaking the kinetic structure into chaotic, unpredictable whitewater chop that severely degrades hydrodynamic lift. The channel. Deep water kinetic bypass. Waves break on shallow reefs. The channel is a localized deep water trench where kinetic energy cannot trip. It provides a mathematically safe, frictionless conveyor belt back to the primary takeoff zone. Line-up triangulation. Geometric spatial anchoring. The ocean constantly shifts. Surfers lock two stationary terrestrial landmarks into a visual grid. This absolute geometric triangulation prevents invisible ocean currents from drifting the rider out of the primary energy zone. The fin key. Mechanical leverage anchor. Fins are subjected to massive shear force. This microhexagonal steel tool exerts exact rotational torque on stainless steel grub screws, physically locking the fin base into the board's structural polymer box. Zinc oxide. Physical ultraviolet barricade. Chemical sunscreens degrade in salt water. Zinc is an unyielding mineral shield. It physically sits on the dermal layer, mathematically reflecting massive doses of high-energy UV radiation away from the skin. The sweet spot. Longitudinal center of lift. Every surfboard has an exact hydrodynamic fulcrum. Standing too far forward creates drag. Standing too far back stalls velocity. Hitting the exact center unlocks frictionless absolute planing speed. Trimming. Laminar plane locking. This is the act of aligning the board perfectly with the wave's horizontal energy vector. By locking the rail into the face, the surfer eliminates drag, achieving maximum effortless kinetic velocity. The kickout. Controlled kinetic ejection. Riding a wave directly into dry sand is catastrophic. The kickout uses a violent shift of rear foot leverage to instantly steer the board over the wave's back, safely exiting the kinetic zone. The nose guard. Blunt force dispersion. A pointed fiberglass nose is a lethal kinetic projectile. This dense silicon bumper cap absorbs and laterally disperses direct impacts, mathematically preventing structural puncture wounds during chaotic wipeouts. Hydrodynamic earplugs. Acoustic membrane barriers. Cold wind triggers abnormal bone growth in the ear canal. These silicon flanges completely block freezing fluid intrusion, while an internal microscopic membrane perfectly transmits essential acoustic frequencies. Aluminum foil tape. Immediate hydrostatic barricade. When fiberglass shatters, the foam violently absorbs water. This highly aggressive aluminum-backed adhesive executes an instant, unyielding vacuum seal, preventing catastrophic waterlogging until a chemical patch is applied. The high-performance shortboard. High-velocity maneuverability. By drastically reducing volumetric mass and surface area, it sacrifices paddling speed for absolute kinetic responsiveness. It fits flawlessly into the tight, violent curves of a steep wave face. The fishboard. Swallowtail fluid release. Designed for weak surf, this wide split-tail geometry increases the planing surface area while allowing water to violently shear out the back, generating massive forward velocity. The pintail. High-velocity stabilization. Engineered for massive hollow waves, the sharp, tapered tail completely penetrates the water column, creating maximum drag-free holding power to prevent catastrophic sliding when moving at terminal ocean speeds. The twin fin setup. Frictionless lateral drive. By eliminating the center stabilizing rudder, water flows freely through the middle of the board. This absolute reduction in drag generates explosive speed, but requires immense physical control. The quad fin setup.
edge-hold acceleration. 4 fins push water through a central channel. This configuration maximizes rail engagement, generating unyielding grip and massive forward thrust to mathematically outrun rapidly collapsing sections of the wave. Kinetic pumping, artificial velocity generation. When wave energy drops, surfers compress and violently extend their bodies, forcing the board up and down the face. This converts vertical kinetic drops into instant localized horizontal acceleration. The cutback, kinetic redirection. Riding too far ahead of the wave destroys power. The surfer brutally carves back into the breaking curl, intentionally returning the board to the primary peak of hydrodynamic energy. The floater, weightless kinetic transfer. When a wave section crumbles, going around it loses speed. The surfer deliberately rides entirely atop the collapsing whitewater lip, utilizing weightlessness to glide over the turbulence. The vertical snap, instantaneous centripetal shear. Pushing violently off the wave's peak. By throwing massive physical weight onto the rear fin cluster, the tail breaks free, reversing direction while throwing a heavy fluid displacement arc. The tube ride, centrifugal barrel entrapment, the ultimate hydrodynamic state. The surfer positions the board entirely inside the spinning cylinder of a breaking wave, matching the exact rotational velocity of the collapsing vortex. The pneumatic spit, compressed gas expulsion. As a massive wave barrels, it traps cubic liters of air. The collapsing water violently compresses this gas, resulting in an explosive high-velocity outward pneumatic blast out the cylinder. The channel bottom, forced linear fluid flow. Deep grooves milled into the tail violently organize water. By forcing chaotic fluid into strict parallel lines, it instantly converts hydrodynamic compression into an explosive forward thrust vector. Polyurethane foam, dense kinetic absorption. Traditional blanks use heavy PU foam. This density provides inherent shock absorption. It naturally dampens the high-frequency vibrations of turbulent water, delivering a smooth, mathematically stable ride in chaotic conditions. Carbon fiber reinforcement, high-frequency structural recoil. Wood stringers fatigue over time. Modern boards utilize aerospace-grade carbon fiber strips. This provides absolute tensile strength, offering a lightning-fast kinetic recoil that violently snaps the board back. The fin cant angle, outward angular tilt. Fins are not perfectly vertical. This outward mathematical tilt dramatically increases maneuverability by engaging the fin's lifting surface earlier in a turn, creating a frictionless pivot point.